All right, hey class. I'm going to record the exam 2 review and hopefully get this posted. You gotta like my animal background here. I'm at my wife's family's cabin, so excuse the beard. On vacation and forgot a razor. So anyway, all right. So let's get into this, and we're going to talk about the test coming up. Okay. Here, go back to the beginning. Okay. Okay, so, oh, sorry. Let me edit this. It's not Thursday and Friday. The test is going to be Monday, July 20th and 21st. And the exam covered along in the book covers chapter 6, 7 to 8.8. Really, it covers everything up till now. The tests are they're kind of comprehensive. You'll have to still remember ideas from the first exam. You don't need to like go on periodic trends or anything like that specifically. But we'll kind of talk about things that I expect that you remember from the first exam, the long exam. Okay, so about 2/3 of the multiple choice require calculations and 1 conceptual questions, and then have some, and those make up about 3 points. There's 4 questions. There's like some sub-questions like A, B, and C. There's 13 sub-questions. And those 13 sub-questions, because they're short answer, have been split into like more than 1 question. So really there's a 38 questions on the test, 25 multiple choice and 30 sub-questions short answer. When you open the test, it'll say there's 75 questions, but that's just because I have to manipulate the short answer questions so that they can be done online. Okay, so for the short answer, what you'll need to know how to define the shape of a molecule. And one thing that's important to note is the difference between electron and electron geometry just has to do with how many groups are around the atom. You ignore the lone pair and look at the shape of the atom, and we'll talk in a sec. But do the lecture on shape, I think it's lecture 12. We'll talk about that more. Bond angles, and then if a molecule is polar or non-polar will be a big part of the short answer questions. Balancing reactions and oxidized and reduced reactants is the other part of answer questions. Okay, so again, you can use the sheets that I give you on, if you go to content and then go to exam info on Learning Suite, there's like 3 sheets, equation sheets, and then 1 periodic. Those are the only 3 sheets there. Pen and pencil and some blank grammar, and that's about it. So the historical average is about an hour and a half. It's about the same as that we did. And then again, there's going to be a 4-hour time limit like there was last time. So no one even got close to 4 hours. Anyway, if you're still taking the test after 4 hours. Okay. And make sure you take it by yourself. Again, there's no notes, there's no internet, no friend, nothing like that. Yeah. Just sit down by yourself in a room and take it in one sitting. Okay. I mean, obviously, if you need to get up and get a drink or something, that's fine. But anyway, okay. And you have 4-hour time limit. Okay. So make sure you're ready when you start the exam, right? Don't accidentally click it because you're curious. As soon as you click it, it's going to start. And so to take it. All right. So these are some previous topics that I've assumed you still know, and we've been using them while we've been learning new material. But this is stuff from exam 1 that's still going to be relevant on exam 2. So calculation concepts, you still have to think about sig figs every time you do calculations, be able to read scientific notation and the prefixes like milli and kilo and stuff like that. And then be able to do conversion factors and unit conversions. In this exam, it's mostly, converting between stuff like that. But those concepts are still going to apply. And then be able to identify and name ionic and covalent compounds. So going from formula to name formula. So an example is on this test, in the first exam, a lot of times I'd say like, write the chemical formula for barium oxide, right? Something like this. Or I'd give you a formula and say, what's the name of this compound? I'm not gonna ask those simple questions anymore because that was exam 1. I'm just gonna assume you know them. So I'm gonna give you a question, barium with oxygen to form barium oxide, okay? And so when I do that, I'm just gonna assume that you know how to write all that out. So you would need to be able to come up with this equation right here from these words. Is a simple metal, which is going to be on its own. Oxygen is always diatomic. And then barium has a 2+ charge. Oxygen has 2 minus barium oxide molecular formula as well. And then you'll have to use that to answer some other part of the question, right? So it might say, let's see if I have, yeah. So it might say like, barium reacts with oxygen to form barium oxide. And then the next part of the question is, how barium oxide can you expect to produce if you start with 2 grams of barium or something like that? So again, that's a little more in depth because you have to be able to, sorry, my hands are blue. I did tie-dye. You have to be able to come up with the chemical equation, balance, and then use that to answer the question. Equation and answering the question. So that's kind of how concepts. I'm not going to like explicitly say, how do you name this or something. It'll just be worked into the questions. Okay. Also remember how to do Lewis structures. Here's just kind of a review for carbon. I know there's like 2 approaches I taught you guys. There's the Lego approach and then the book approach. The Lego approach works really good with simple covalent compounds, but the book approach works, I personally think it works better with polyatomic ions. So again, you do what you're comfortable. If you're using the book approach in this one, you could say carbon has 4 valence electrons and oxygen has 6 valence electrons times 3 is 18. We have 2 minus charge, so we add 2. 4 plus 18 plus 2 is 24 total valence electrons. So then you draw all the atoms connected by 1 bond, right? Then you start filling it all around the most electronegative atoms. Let's see. And at this point, we've used all 24 electrons, but carbon doesn't have a full octet, so we need to share electrons, right? So we share electrons and create a double bond between the carbon and the oxygen. I'm pretty much done. The easiest thing to do is just cover it in brackets and put the overall charge outside. So I might ask in this, in the last test I just said, what's the Lewis structure for carbonate, right? But this question might not say, what is the shape around carbon, or what is the shape of carbonate, right? And so that question, although it just asks for the shape, it requires you to do a Lewis structure because you can't do the shape unless you draw the Lewis structure first. So again, this is where you're going to be coming back to concepts from exam 1 in order to answer these questions. So if we're looking at the shape for carbonate, we can see there's 3 electron clouds or electron groups around carbon. So that means it's going to have a trigonal planar electron. And then the shape is going to depend on the lone pairs. And there are pairs, the same as the geometry, and the angle is always 120. Okay, so review those for sure. This Vepper theory, again, is just saying electron clouds are going to move as far apart from each other as possible, and that's what creates those different angles that we observe. This dictates the geometry. So for electron clouds, 109 degrees is how far apart they can get, those clouds can get. Trigonal planar is 120, and linear or 2 electron clouds is going to be 80 degrees. Okay, so when we come back to the idea where electron G solely depends on the number of electron clouds, and then the shape name ignores the lone pairs. So beryllium chloride, okay, this has 2 chlorides bound to beryllium. So we have 2 electrons, there's no lone pairs. So we're going to have a linear electron geometry and a linear shape. Let's see, we got boron trifluoride, has 3 fluorides coming off of boron, and there's no lone pairs on boron. So you have a trigonal planar shape. Sulfur dioxide, it's kind of a bad drawing, but it would look like this. Oh, sorry. Wait, hold on. Yeah, sorry. We go through the whole process, but it should look like this. Okay, that looks right. Okay. So you have electron groups around sulfur. Okay, so that would be a trigonal planar electron geometry. But if you ignore these lone pairs, you can see that the shape just looks like this shape. Okay, all right. Moving on. So the example are when you have 4 electron groups, right? You can have groups are going to have a tetrahedral electron geometry. But depending on the lone pairs, so this one has the lone pair up here. So if you just look at the bound atoms, it looks like up there, kind of middle. Then in water, we have 2 lone pairs. So the atom looks like this, and that's the bent shape. Okay. In your book and stuff, you might see. Okay. Don't worry about like 107 if it's trigonal pyramidal or 105 if it's, I don't really care that you know these just in general are going to be around 109. Okay. Okay, so electronegativity we talked about. There's different electronegativity values, and the larger the value means the more they want to hold on to electrons. And so we learned a more true definite covalent compounds, right? So what we looked at is these kind of divisions. So if the electronegativity between 2 atoms is between 0 and 0.4, it's considered nonpolar. So between 0 and 1.8, it's considered polar. If it's greater than 1.8, it's considered ionic, okay? So those are what you need to know. I think I mentioned, but I was like, wait, right, that'd be hard. I'll make it either something. Okay, that way you know exactly what it is. So this is telling us the electronegativity difference of a single bond. This tells us if a bond is polar or nonpolar, which is in the covalent category, or if it's ionic, right? So then you can use that information to determine if a molecule is polar or nonpolar. Okay. So if each bond is nonpolar, then the molecule is nonpolar, right? We talked about that. But if it contains polar bonds, then there's some things that. So cancel out the dipoles. And we talked about oxygen is a polar bond, but the electron movement will just cancel each other out in carbon dioxide. and get a net movement of 0 across the molecule. So that's a nonpolar molecule, okay? These are nonpolar. These have polar bonds. All these have polar bonds. But overall, the dipoles cancel out. So basically, if you have all of this, you're just going to cancel out, okay? All right. Asymmetric, so it doesn't have the same thing around it, like any of these, right? So you have in ammonia, but then you also have a lone pair, so it's not symmetrical there, because oxygen isn't bound to all hydrogens. It's bound to 2 hydrogens and some lone pairs, so it's asymmetric that way, okay? You could, don't let you draw a line down the middle and say, oh, it's symmetric on both sides, right? And while it does have a plane tree, so it's not symmetric. And so if there are planes where it's not symmetric, that means that it's going to be a polar molecule. All right, or just think if it's connected to different, if the center connected to polar, it'd be polar. Let me correct that. If the centrum atom is connected to a bunch of the same things, then it would be nonpolar. Okay. So now moving on to intermolecular forces. Hopefully you're seeing how these all kind of connect, right? The type, whether the molecule is polar or nonpolar, is going to determine the type of intermolecular forces between 2 different ionics, the strongest, and then you go down to hydrogen bonds, right? These are where you have hydrogen bound to a nitrogen, oxygen, or fluorine, and there has to be a lone pair on these, which there almost always is. Dipole-dipole, so that's if you have a polar molecule, right? This is if you have an ionic molecule. And then if you have a nonpolar molecule, you have dispersion. So we've talked about 3 types, right? You have ionic molecules, which means you have ionic intermolecular forces. You can have polar molecules, which means you have dipole-dipole. And you can have nonpolar, which means you have dispersion. Hydrogen bond is kind of this special type of polar molecule. So if you have a molecule where it's hydrogen bound to nitrogen, oxygen, or fluorine, it's a polar molecule, and because of that special requirement, it also contains hydrogen bonds, okay? And this graph just shows the relative strength between different types of their forces. All right, so then we talked about chemical reactions. So you should be able to correctly balance a reaction and include the phases for the reactants and products. And this is a big sticking point for a lot of people. They're good about this. I'll talk about this in the next slide, what you need to know, and then hopefully you don't feel so stressed out about it. So if I do 2 reactants and I tell you what kind of reaction it is, like if it's combustion or decomposition or combination, right, you should be able to predict the process of that reaction. And then if it's on certain reactions where you have oxidation and reduction occurring, I might ask which of them was oxidized or which was reduced, and you should be able to identify those. Okay, using both sets of rules. So this is the oil rig, and then this would be if you're dealing with covalent compounds, it would follow these rules here. So here the way to remember these up here is just the oil rig. And then down here, what I remember is just oxidation is gaining oxygens. Okay, and that's how you can remember these ones. Cool. All right, so talking about phases, we say include the state or the phase. So if you're dealing with diatomic gases, which are any of these here, they're obviously gases, right? It's a diatomic gas. Bromine's a liquid, iodine and carbon are solids. These are all at room temperature, by the way. So if the question on homework, sometimes it will tell you exactly what state it is, but if it doesn't give you a lot of, these are the assumptions you make, okay? And this is what I would accept on the test, are these, right? Metals are solids, except mercury is a liquid. That's the only exception for metals. And then if it's a salt or an ionic compound, this is where things get confused. And I would accept either aqueous or solid at this point, because we haven't learned when one is aqueous or one is solid. 90 or 95% of the time, if it's an ionic compound, it's going to be aqueous. So you can just put that for now as your default. And later on in the semester, we'll talk about when these are solids. What this means is, like, for table salt, right, or sodium chloride, they're a solid. Like, if you see salt, it's a solid, right? But as soon as you put it into water, it dissolves. And so reactions are being done with ionic compounds. They're almost always being done in water. And when they're being done in water, they're not really solids. They're in this aqueous phase where they're dissolved by the water. And that's why they're almost always labeled as aqueous. So you just put aqueous for now. And if it's an ionic compound, and we'll talk about some of the differences later. And then covalent compounds, I'm not going to expect you to be able to predict these at all. I mean, you know, maybe carbon dioxide would be something you should know as a gas, but for these, I'll be very explicit in the question on what it is, or I may just not even go there at this point. Anyway, okay. All this to say, don't stress out about phases, right? Don't spend the bulk of your time studying phases when you're studying for the test. I looked through the test today, and there isn't even like that many questions where this is even that relevant. I think a lot of times it's just given to you. Know these that are on the slide, right? But don't stress out about it too much. I'd worry about learning stoichiometry and gas laws a lot more than this. Okay, so again, be able to recognize which reactant was oxidized and reduced. We already talked about this. So there's some examples for you. Stoichiometry, okay. This is where we're getting to that stoichiometry map, which I think I just showed at the end of this lecture. But remember Avogadro's number, right? The mole is Avogadro's number, and that means it's just a certain quantity of something. Like a dozen eggs is 12 eggs. Well, 1 mole is going to be 6.022 times 10 to the 23rd items of what it is. Molar mass, that's found on the periodic table, and that's in units of grams per mole. So that's what we use every time we convert between grams and moles. Balanced chemical equations. Okay, those give us the mole ratios. They have the integers at the front. And so we can go from grams to moles, moles to grams, right? In my map, I say from grams of A to moles of A, over to moles of B, and then over to grams of B, right? We did this like a bazillion times. Anyway, remember the percent yield calculation. So you're gonna have actual yield over theoretical yield, gives you your percent yield, okay? Be able to do the reaction calculations, and if you're, for any of these, if you're struggling with them, go back on Mastering Chemistry, and I have like tutorial, I think they're labeled like tutorial or practice problems or something. So you don't need to redo the homework. I mean, you can if you want, but you've already seen the problems, so it's not that helpful. But I give you a bunch of other problems to practice that aren't required or anything. You can go on Mastering Chemistry and get, if you need more limiting reactant problems, go on there and practice those, okay? Okay, and this is how you do it, right? You calculate the theoretical yield for each of the reactants, right? How much product you could produce, and then whatever produces the smallest theoretical yield is the limiting reactant. And yeah, if you have more questions, practice or go back to the limiting reactant lecture, and I go into it in a lot more depth, okay? Okay. All right, energy. So we talked about activation energy and how reactions work. We talked about the difference between endo and exothermic reactions. So a negative delta H indicates exothermic, and we consider heat a product, and the opposite is true for endothermic, right? And then we use stoichiometry and delta H to figure out how much heat is produced given a certain amount of reactant, okay? All right, so here's an example, right? We have this chemical equation has a negative delta H. So heat is released, right? So we can consider heat as a product. And we say that we have 100 grams of sodium and 100 grams of chloride. What is produced and what is left over? So how much product is produced and how much reactant is left over, right? So you could try and pause the video and work this out. You should have enough information right here to do all this. Okay. So using 100 grams of sodium, we can convert from grams of sodium to moles of sodium. And then remember, we can go from moles of sodium over to energy, just using delta H, right? This tells us how many kcal. So we can say that 2 moles produces, 196 kcals of energy. Theoretically, with 100 grams of sodium, we should be able to produce 426 kcals of energy. With 100 grams of chlorine, we'll be able to produce 276 kcals. So you can see that chlorine is going to be our limiting reactant because it limits how much energy we can produce. So then you can go from grams of chlorine over to grams of sodium using the stoichiometry, and tells us how much sodium is used. So that's about 65 grams. We started with 100 minus 65. We have about 35 grams left over after the reaction's done. Okay. Hopefully you're able to do that. If not, like I said, go back and practice some of those limiting reactant problems. And we can also figure out how much sodium chloride is produced. We know chlorine's our limiting reactant, so we'll start with that, and it'll tell us how much sodium chloride is produced. All right, move into gas laws, right? It's kind of the last part. So there's a bunch of different pressure units. You should be able to convert between those. And look on the equation sheets while you're studying so you know exactly what is going to be given you on the equation sheet and what you might need to learn. And you always convert the temperature to Kelvin for gas problems, okay? Just always convert it to Kelvin. Don't even try it in Celsius. Vapor pressure, again, we talked about this in depth in the vapor pressure lecture, but depends on temperature. So if you have a higher temperature, you have a higher vapor pressure. And the liquid boils when the vapor pressure equals the external pressure, right? So when you're at a higher altitude, you have a lower atmospheric pressure. You don't need to heat it up as much because the vapor pressure doesn't have to get as high in order to boil. Okay, and that's kind of the idea that we talked about in that lecture. We also talked about part pressures in the end there. The sum of the partial pressure of each gas individually is going to be equal to the total pressure of gases in a container or a certain area. All right, and then remember, gas laws are all variation of the ideal gas law. I showed this derivation a few times. But you can get this, right? The ideal gas law is PV equals nRT. You can read this as PV over NT equals R. And R is always the same. So P1 V1 over N1 T1 should equal some other set of P2 V2 over N2, because these always equal the same thing, R, okay? And so then depending on what is held constant, right? If moles and temperature are held constant, then you get Boyle's law. I believe this one's Boyle's law. And not really that, you should know kind of in general what the laws are and a person or whatever who discovered it. But as far as just remembering what the law is, like if you're doing a certain problem, the problem may not ask for the name or something of the law, but just know what's held constant and you can figure out all these different gas laws, right? Okay, these are all the different ones we looked at, depending on what's held constant. And again, is as you're reading the question, write down what you know and what you don't know, and it will basically indicate right there for you which gas law to use, right? So if you're reading a question and you have P1 equals some number and T1 equals some number and P2 equals another number, and then it asks for temperature. Okay, you obviously need a law that just has P1, T1, P2, T2. Okay, so that's going to be this law here, right? Okay. And that's how you determine which law to use. All right, and converting volume to moles, we talked about a few different ways to do this. At standard, okay, use the 22 per mole, right? That's for any other temperature and pressure, you can just do PV equals nRT, right, to figure out the number, to convert from volume over to moles, okay? All that, right? We talked about, and the pressure and the temperature are held constant. Then, okay, so I should have that in here. And if P and T are constant, right? This is when we can use Auger's law. The mole to mole ratio is equal to volume ratios, okay? And then, okay, so here's that stoichiometry map, right? So if you have a gas at STP, again, you need 4 liters. Not at STP, you can use PV equals nRT. And then the other, sorry, not from there. Back up. The other one, the kind of the shortcut, I guess, is going from volume of A over to volume of B, okay? And then this is Avogadro's law, which says that the volume ratio is equal to the mole ratio, okay? So you can use mole ratios, like the molar ratio. Technically, it's the volume ratio. And that would convert. It's kind of a shortcut. Okay. 2 examples here at the end, but really the purpose of this lecture is to tell you what to know. It's not really to go over everything, because that's what all the lectures are for. So if you need to go over anything again after going through this lecture and seeing what you need to know, go back to the lectures on the YouTube, and you can work it out there and problems on the street. All right, so here's an example. We have what volume of carbon dioxide gas is released at 3 Celsius and 0.85 atmospheres, and 2 liters of ethane is burned. Okay, so if we're using, like, if you're looking at the stoichiometry map, we need to go from liters of ethane to liters of carbon dioxide gas, right? So these are all gases, and we just have one temperature and one pressure. So we should be able to use the shortcut on this one. So really we just need to say we have 2 liters of ethane. The ratio is going to be 2 liters of ethane to 4 liters of carbon dioxide. About the answer. If you tried the problem, you went through a different way, right? You could convert these liters to mole using the ideal gas law, then use the mole ratio, and then convert back from moles to liters using the ideal gas law. It's just, it all works. One's just a little easier. All right, the next example. Say how many grams of water are consumed when producing 1.5 liters of ammonia at 2.5 atmospheres and 85 degrees Celsius. Okay, so in this case, we need to go from liters of ammonia over grams of water, okay? So we need to go from volume of A to moles of A to moles of B to grams of B, right? A to moles of A, we're not at standard temperature and pressure, so we need to use the ideal gas. So you can see this on the stoichiometry written down or something. Moles of A to moles of B's is just the molar ratio, and then you have the molecular weight or the molar mass that takes you from moles of B to grams of B. Okay, so First, we convert from volume to moles using the PV equals nRT. This is just the rearranged version. Okay, so now we start with 0.128 moles of NH3. We can use the molar ratio then to convert to moles of water, use the molar mass of water to convert to grams of water, and we get our answer. So again, that's just kind of an overview of what you need to know, and continue studying, identify what you don't know well, and go back to the lectures and the homework and practice it. And email me if you have questions, and I will try and respond as soon as I can. So, alrighty, have a great time.